Welcome to today's notes on Ka and Kb. So, yep, you guessed it. Because we have K values here, we are dealing with equilibrium, and we are dealing with equilibrium for acids and bases. So, how do we deal with this? Well, before we talk about that, we're going to talk about the difference between strong acids and bases and weak acids and bases. So, to start off with, strong acids and bases, they're considered strong because they completely dissociate in water. But what does that mean, dissociate? Well, it means that they break apart into their ions. So the ions completely break apart for strong acids and bases. So here is a video that will help demonstrate what this means. Here we'll show you the dissociation of a strong acid. We have hydrochloric acid in the little beaker, and in the big beaker we have water. So when we start the animation, we add the hydrochloric acid to the water, and you'll see that all of the hydrogens from the hydrochloric acid leave the chloride ion for the water, forming H3O plus and Cl minus. There are no more HCl's present in the big beaker. So an example of a strong acid is hydrochloric acid, and as you can see, hydrochloric acid breaks into H plus and Cl minus. And you'll notice I said that we were dealing with equilibrium before, but here we only have a one direction arrow. So that means that we are not dealing with equilibrium. So no equilibrium for strong acids and bases. And an example of a strong base is NaOH, or sodium hydroxide, and that breaks up into Na plus and OH minus. And again, it's not equilibrium because we have that unidirectional arrow. Now, when we're dealing with strong acids and bases, finding the pH of these is really simple, and that's what we talked about in our pH and pOH notes, where the molarity of the acid is equal to the molarity of the H plus ions, and the molarity of the base times the number of OHs is equal to the molarity of the OHs. So then you just plug these into your pH equations, and you can find your pH or your pOH, and it's pretty easy, just like we did in our pH pOH homework. Now, what about weak acids and bases? Weak acids and bases are slightly different. They're considered weak because they only partially dissociate in water. And again, this dissociate means that they break apart. So that means we have a case of equilibrium here. So most ions stick together rather than break apart. That means that we have an equilibrium situation, and I'll show you what this means with the following animation. And here we have an example of what happens when a weak acid is put into water. So in the little beaker we have a weak acid, and it's any weak acid because it's HA. And then the big beaker, again, we have water. So we're going to start it, pour all of the HA into the OH minus, or the water, and what will happen, what you see happen, is only a couple of the hydrogens from the HA have moved onto the water, and we're left with many HA in the solution. So that's why we have an equilibrium situation where we have both products and reactants all in one beaker. Okay, so an example of a weak acid is hydrofluoric acid, and hydrofluoric acid is HF. So if we add that to water, we get F minus plus H3O plus. You can also write this as HF is in equilibrium with H plus plus F minus. Either one of these is acceptable. Just remember that our hydronium ion is equivalent to our H plus. The H plus is just shorthand notation for the hydronium ion. And our base, an example of a weak base, is ammonium. And ammonium reacts with water to form ammonia reacts with water to form the ammonium ion plus hydroxide. So when you're writing it and you include the H2O, remember that that's a pure liquid. Everything else is an aqueous substance. And the reason that's important is because when we're writing our equilibrium expressions later on, it's important to remember that because pure liquids do not go into our equilibrium expressions. So how do we calculate the pH and pOH of weak acids and bases? Now, before we go into that, we also need to talk about our equilibrium expression. Ka is what we use for the equilibrium expression for the acid dissociation, and Kb is the base dissociation. So in this case, we would have Ka for the HF is equal to H3O plus times F minus over HF. And for the base, we would have a Kb, because that's a base, is equal to NH4 plus times OH minus over NH3. And again, we leave water out because it is a pure liquid. Now, what is the value of our Ka or our Kb tell us? Well, the bigger the K value, the more dissociation there is, because we have more products, and that's more of our ions. So it means that they broke apart more. And so the bigger the K value, that means the stronger the acid, or the stronger the base. So so bigger K equals stronger acid or base. Now, how do we find the pH or the pOH of a weak acid or a weak base? Well, let's start off with the pH of a weak acid example. So first thing we want to do is write the dissociation reaction. So we have here, what is the pH of a 0.05 molar solution of acetic acid with a Ka value of 1.8 times 10 to the negative fifth? So write our dissociation reaction. So acetic acid is HC2H3O2 is in equilibrium with H plus C2H3O2 minus. Okay, so we did step one. Write the K expression for this. Okay, because this is an acid, it's going to be a Ka. So Ka is equal to H plus times C2H3O2 minus divided by HC2H3O2. Okay, so we wrote our K expression. Now we create an ice table, and we're going to use the part from step one to do that. Okay, so our initial concentration of our acetic acid is given to us as 0.050 molar. Because we are not given the H plus or the acetate ion, we're assuming that those are 0. Then the change, well, because this side is 0, it will gain. That means this side has to lose, so it'll be minus x because it has a coefficient of 1, plus x because it has a coefficient of 1, and plus x because it has a coefficient of 1, giving us an equilibrium of 0.05 minus x, x, and x. Okay, so we created a nice table. Now we're going to solve for pH using equilibrium values. That means we have to solve for our equilibrium values. So the way we do that is we take x squared over 0.05 minus x is equal to our Ka, which is given to us as 1.8 times 10 to the negative fifth. When we multiply both sides by the 0.05 minus x, we get x squared is equal to 9 times 10 to the negative 7th minus x minus 1.8 times 10 to the negative fifth. Set that equal to 0. We get 0 equals x squared plus 1.8 times 10 to the negative fifth minus 9 times 10 to the negative seventh x. Plug that into your quadratic and we get that x is equal to 9.4 times 10 to the negative fourth. Well, x is the same thing as our H plus at equilibrium. So that's also going to equal our H plus concentration. And because we have to worry about units, that's molarity. So now we have to solve for pH. Now that we have the equilibrium value of our H plus concentration, we're going to solve for pH. And so pH, remember from the pH notes, is the negative log of our H plus concentration, which is equal to the negative log of this. So the negative log of 9.4 times 10 to the negative fourth, which equals 3.03. And there's our answer. Now we're going to give you an opportunity to solve out a base one in your group. So after you get this copied down, pause the video, work it out, and then come back for the answer. So what is the pH of a 0.34 molar solution of methylamine, which is a formula of CH3NH2? And the Kb is 3.7 times 10 to the negative fourth. So again, we're going to start out by writing our dissociation reaction. So because this is a base, we know it's a base because the B here, the Kb tells us it's a base. So that means that we have to add water. So H2O plus CH3NH2 is in equilibrium with OH minus plus CH3NH3 plus. And we know that this gains the hydrogen because it's acting as a base, and a base is a proton acceptor. And because it's a proton, it's getting an H plus, which means we need to include that in the charge. Okay, and then our Kb expression is going to be CH3NH3 plus times OH minus all over CH3NH2. And we do an ice table. And because, as we said before, water is a pure liquid, we're not going to look at it at all. And now we fill in our ice table. So we know that the methylamine to start out with is 0.34 molar. And because we're not mentioned, the hydroxide and the cation are not mentioned, we're going to assume that they have a 0 concentration. And then this will be minus x, this will be plus x, this will be plus x. So we have 0.34 minus x, x, and x. So now we plug these values in. So we have x squared over 0.34 minus x is equal to 3.7 times 10 to the negative fourth. When I distribute this out, I get x squared equals 1.26 times 10 to the negative fourth minus 3.7 times 10 to the negative fourth x. Set it equal to 0, and I get x squared plus 3.7 times 10 to the negative fourth x minus 1.26 times 10 to the negative fourth equals 0. And after I plug it into my quadratic, I get x equal to 0.011 molar. Now remember that our x here is our OH minus concentration here. So 0.011 molar OH minus, well, if I take the negative log of that, I'm going to get POH. So POH is equal to the negative log of 0.011 And so when I get that, I get 1.96. But it's asking me for my pH. So now that I have my pOH, I know that pH is equal to 14 minus pOH. So my pH is equal to 14 minus 1.96, and that equals 12.04. And there's my answer. If you have any questions, please ask one of your classmates that understands it, or rewatch the video, and good luck with your homework.